Hi, we are going to move on to molecular orbital theory. Just get the camera set up. So we're going to move from valence bond theory, which was the first quantum mechanical theory of bonding, to molecular orbital theory, which is used a lot more now. Okay, so I'm going to go back to using the book as a note. Hopefully that works for you. You have your book in front of you, so I know this probably isn't something you can really read, but at least you can see which area I'm looking at as you look in your own textbook. So why do we need to know this? Molecular orbital theory is the basis of almost all computational techniques for the prediction and analysis of properties of molecules. So if you're using any software whatsoever to understand energies, geometries, spectra of molecules, you're using molecular orbital theory. So molecular orbitals are wave functions that spread over all the atoms in a molecule, and each one can accommodate up to 2 electrons. So we see when we create molecular orbitals, they have the same properties as atomic orbitals. They follow Hund's rule, Pauli's exclusion principle, so we'll fill them in the same way that we filled atomic orbitals. So when we look at the very simplest molecule, H2+, we think back at how we built the periodic table. It was by solving the hydrogen atom and then using those orbitals as approximations for all other electrons. And that's what's often done. H2+ is the simplest molecule it is. So hydrogen molecule, but you take 1 electron away, so you only have a 1 electron bond. Turns out this is the only molecule that can be solved exactly, and exactly is only exact within the Bohr-Oppenheimer approximation. So using the Bohr-Oppenheimer approximation, you can exactly solve for the molecular orbitals of H2+, but nothing else. So once again, we're going to have to think about approximations as we move through understanding this theory. So it has a face sort of as valence bond theory only in how we solve Schrödinger's equation. So we solve Schrödinger's equation by starting out and assuming that a molecular orbital can be written as a linear combination of atomic orbitals. So we can say that, for example, if this is the B nucleus and this is the A nucleus and we have our electron, we can use as an approximation to our molecular orbital, so this is our MO, to be a linear combination of a 1s orbital on the B atom and a 1s orbital on the A atom. And so that linear combination of atomic orbitals is used as an approximation of a molecular orbital. And if you take 367, you'll see that you're not just going to stop there, you're going to try to perfect it, but that's your starting point. So you can add and you can subtract those orbitals to get the molecular orbitals. So if it's a symmetric molecule, then the combination is going to be the same, or the contribution. So the contribution from an orbital on B will be the same as on A because there isn't any asymmetry. So Ca will equal Cb, and we can just then talk about this linear combination being a sum and a difference of the s orbital on A and the s orbital on B. And so when we take the positive combination, we get a sigma orbital. So we get something that looks like this figure 1 on page 402, whereas the 2 orbitals come together, they both have the same sign. And so you're going to have constructive interference in between the nuclei. The waves are going to add to get bigger peaks. And so it looks similar to this picture at the top of the page, figure 2. We have our 2 nuclei. If these are the same sign, they're going to add to make more electron density. in between the nuclei. And when you look at it, cut it across the bond axis, it's going to be circular symmetric. So it's going to be a sigma bond that we form. And when we think about this bond, it's very similar to thinking about the valence bond theory. Why do we call that a bond? Why is it a bond? Why does it hold the protons together? And the three contributions are the same as they were from valence bond theory. So there's an accumulation of electron density in between the nuclei that helps hold the nuclei together. We remove electron density from close to the nucleus, and that raises the potential energy, so that's a negative impact. But also the kinetic energy goes down as a result of the electrons being able to spread out over more space, so that makes it more energetically favorable, lowers the energy. So this overlap integral, SAB, is called the overlap integral, and it's really just the sum of the wave functions in between the nuclei. So the product of the wave function 1s on the A atom and 1s on the B atom. And so that's going to tell you essentially how strong the bond is, how much overlap there is between the two nuclei. So when we look at these integrals, well, we haven't looked at those integrals. You can do self-test B1 and base it on the brief illustration and then come back. But all you're thinking about is how the integrals change as the distance between the nuclei change. So what you're going to do is you are going to solve Schrödinger's equation at a certain R value, and you're going to get an energy. You're going to do that over and over and reset R. That's what Born-Oppenheimer approximation says. Rather than solve for everything moving and a wave function for the nuclei and the electron, you're going to use the distance between the nuclei as a parameter. Solve for the energy, lowest energy, lowest energy. You're going to get a potential energy curve like this one. And the bottom of it would be the equilibrium distance at which the atoms exist, and then the distance up to where it goes to infinity in the internuclear distance. That's going to be how much energy it takes to dissociate the molecule. So then when we think about, that's the bonding orbital that we just looked at. The anti-bonding orbital is when you take the difference between the two. Let's see the pictures on the next page. Yeah, they should make that a little more clear. I mean, generally you would color this red and this blue to show that if you're subtracting the two, then this orbital would have a negative sign everywhere that this one has a positive. And then when you add them together, you're going to get a region in between the nuclei where the positive and the negative exactly cancel each other in destructive interference. So you get a node between the nuclei. So that helps to pull the nuclei apart. So it's called an anti-bonding orbital. It's still a sigma, so it's still going to be a sigma. So our first one, the sum, is a sigma bonding. And the second one is still sigma, because if you cut that across the bond axis, it's still circular, but it's anti-bonding. So we'd call that a sigma star bond. So bonding and anti-bonding. And so when you think about the hydrogen molecule, the H2 plus, the hydrogen ion molecule, you have one electron, and that's different than valence bond. Valence bond said you form bonds by overlapping orbitals that each had one electron. Here you could have a bond formed with one electron, and it's only in the bonding orbital because that's the lowest energy. So the H2 plus would be a 1 sigma, would be its electron configuration, a 1 sigma 1. So you could draw an electron configuration just like you draw an electron configuration for atoms, labeling the orbitals slightly differently, but similar. Sigma pi is similar to S and P. So just a little bit about notation. Whenever you have a homonuclear diatomic, you can talk about inversion symmetry. So with the bonding orbital, if you are standing here and you go through the center of the molecule to the other side, exact same location, it's going to have the same sign. So we call that Gerard. That's just the German word for inversion symmetry. And then you have the anti-bonding one. This lobe over here has a negative sign, this has a positive. So when you go from here over to here, it changes sign. And so that's called ungerard. So often you'll see those terms in spectroscopy, especially when they're talking about the states that are allowed. So now the chemical bond can be one electron or two electrons, or it could be a sum of more electrons in more molecular orbitals. So we have for this is just the molecular orbital diagram. It could be used for hydrogen or helium, anything that only has just one s orbitals. So you'd have a 1 sigma and a 1 sigma star. When you're making H2, the 2 electrons go into the bonding orbital. So this is a molecular orbital diagram. Shows you that relative to the s orbitals on the hydrogen separate, when you form that molecular orbital, you go down in energy. And so because you only need room for 2 electrons, they'd go here. If you tried to make the helium diatomic, you'd need 2 here and 2 here. And when you think about what the bond order is for that, the bond order is always a bond is defined as 2 electrons shared. So if you take all of the electrons in bonding orbitals and if you notice, when they go into bonding, they have lower energy, but when they go into anti-bonding, they have higher energy. So that essentially cancels, and you're back at not having any bond at all, that it'd be just as well to leave the molecules separated. So number of bonding electrons minus the number of anti-bonding. And then we just multiply it by 1/2 because 2 electrons make 1 bond. And that's probably pretty familiar from Gen Chem. So when we look at whether or not a molecule is going to be stable, if it has more electrons in bonding than anti-bonding, it's probably going to form a stable molecule. So let's just take a minute to create a diagram for something bigger. So I'm going to then I'm going to go to some software that's super easy to use. It's called Webmo. So if you ever wanted to do this, well, I'll show you in a second. Just go to Webmo and sign in as a guest. And I'll share again. And let's just make a molecule. So let's create the molecular orbital diagram for nitrogen. So I'm going to build the molecule on those 2 nitrogens together. I'm going to clean up the geometry, which just means I created this geometry. It could be so far off that the calculation could never work. So I make it from what it already knows about nitrogens closer to the truth. And then I do a Gaussian calculation where I'm going to get a better geometry. Shouldn't take too long. Next, I'm going to take that geometry. So I'm going to click on that job. And I'm going to start a new job with this geometry. Now I'm going to calculate the molecular orbitals. So when I do that, now I will get pictures of the molecular orbitals, and I can think about what they're called and what their relative energies are. So if we go down here, we have the valence electron orbitals. Notice orbitals 1 and 2 aren't there. You can look at those. Those are the inner shell orbitals that just have the 1s electrons for both nitrogens. So let's look at those that go into a orbital diagram. This first one, you can rotate it, and you can see that it's circular, so it's a sigma, and it's the lowest energy. And the lowest energy, I'm going to write this out while I do this, and then I'll show you because I can't share both screens at the same time. So I have 2 electrons in this orbital. So if you look over here, gives you the energy of negative 15.691, and it tells you there are 2 electrons, and it's sigma. 1 sigma bonding because there's no node. When we look at the next one, now there's a node between the 2. Whoops, I'm on the wrong, oh. Oops, that was 3 I did. So as I said, these 2 are the inner shell s electrons. This is the first one that's taking part in bonding, so it's a 1 sigma. And that is not at negative 15, that's at negative 1.488. A little bit higher in energy is this one. So think about it. What kind of orbital is that? Does it have circular shape when you cut it across the bond axis? Yes. So it's sigma, but it has a node between the nuclei. So that makes it a sigma star. So you have 2 electrons in an anti-bonding orbital. Come up a little bit higher at negative 0.632. And that also has circular symmetry or shape when you cut it across the bond axis. There's no node between the nuclei, so that's a 2 sigma. You could think of that as being a result of the overlap of 2 p orbitals head on head, and it's occupied with 2. Then we get this guy. You can rotate it and quickly see that that is a pi, so it's a 2 pi, and there is no node between the nuclei, so it's bonding. It's at negative 0.620. And notice that the next one has exactly the same energy, so you have degenerate pi molecular orbitals, and they each have 2 electrons in them. So stop that share and come back and share this again. So the orbital diagram that we just drew looks like this. So for nitrogen, 2 electrons in a 1 sigma, 2 in a 1 sigma pi, 2 in a 2 sigma, and 4 in a 2 pi. So if you get the bond order, it would be 2, 4, 6, 8 minus 2 divided by 2. And so you'd have a bond order of 3, which is what we predict. So the reason I'm doing this is so that you're totally aware that in order to get these molecular orbital diagrams, you have to have a computer to calculate them. So when we're looking at homonuclear diatomics, we're going to construct molecular orbitals by forming linear combinations. And that's what the computer starts with, but Gaussian then makes them better. So it starts with linear combinations and then perfects them by using something called the variational principle. Then we're going to accommodate all the valence electrons. In Gaussian, it told us how many electrons were in each orbital, but I would just have to put into the orbitals all my valence electrons using Pauli's exclusion principle, meaning each orbital can only have 2, and Hund's rule, which says if you had 2 of equal energy, you'd put 1 in each first, which is number 3 and number 4. So let's do it exactly like use atomic orbitals. And these are then just going through different molecular orbital diagrams, because everything's going to have a different ordering of the energies. And showing you then the relative energies for all of the period 2. So each of these molecular orbital diagrams would have been calculated with some sort of molecular orbital calculation in Gaussian games. There are all sorts of options. And as you read through that and do the self-tests, I think it'll look very similar to what you did in Gen Chem, except now hopefully you have a little better idea of where those diagrams come from. So the criteria for building molecular orbitals: use all available valence orbitals from both atoms. So that's what the software does. It takes p orbitals if it needs them, s orbitals, maybe d. Consider all atomic orbitals of similar energy of the same symmetry around the nucleus. Those are decisions the computer makes. Build the sigma and pi orbitals from the atomic orbitals, and then place the electrons in to each of those orbitals using the same rules that you use for atoms, Hund's rule and Pauli's exclusion principle. So that is molecular orbital theory. Get a much better picture of it if you take 367, where we'll look a little bit deeper at exactly what Gaussian's doing. But at least now you should have a better understanding of how quantum mechanics is necessary for understanding bonding.